正在录制此会议。
Okay, good morning everyone. Hope you enjoy the weekend today. And as I mentioned, I will be abroad this week, so it is a good timing for me to upload this video online. And hope you can have this lecture and rehearse it several times. So today we are going to talk about the first transistor together with the MOSFET. So before we talk about the MOSFET, we want to first introduce the scheme in which we have the metal insulator semiconductor connection. So you can think we already talked about the first transistor using bipolar junction. And this bipolar junction transistor is basically with a three-terminal transistor. And as we will come up with a really similar transistor using the metal insulator structure. So we previously mentioned that if you want to connect with the metal and the semiconductors, there will be like metal junction. So we get the Schottky barrier and the ohmic contact. And here you can consider if there's additional layer that we call the insulator in between the metal and the semiconductor. And at that time, the semiconductor is again connected with ohmic contact. There will be some different performance and behavior. So this structure is first proposed as the voltage-controlled resistor. So it can be considered as the capacitor with a variable capacitor in 1959. And these systems that silicon oxide is the most ideal and the practical metal insulator semiconductor structure. And I thought maybe some of you are working with different material like the 3-by material. And for 3-by materials, I think you get better mobility, you get better current. But the problem is that typically it's really hard for us to get an insulator on top of this 3-by material. So that is the power of silicon. That's the reason why people looking for CMOS compatible process using silicon and the silicon oxide. So ideally, it can be easily fabricated with the semiconductor together with the insulator. And then so we can connect the two metal on both the insulator and the semiconductor part to change the capacitance, because we get the insulators, we get a different charge separation in between the metal and the semiconductor. So that will be a way to control the capacitance, but not only for this capacitance control. We will later talk about why and how we have the carrier accumulations within this structure. And the later by combining with the source drain, we will realize the complete CMOS transistor using this architecture. And next, we will first introduce the assumption. So with this metal insulator semiconductor connection, typically you have two assumptions. The first assumption is that the only charge existing inside this material, this IC structure, is in semiconductor and the metal surface. So there will be no trapped charge in between the dielectric material, and there will be no surface in charge within this defect material. And also, these charges should be equal with opposite side, work as a capacitance. So you can think if we have the driving voltage on both sides onto the metal and the semiconductor, the charges are separated with each other depending on what is the voltage side you apply. So we get positive charge in metal, there will be negative charge in semiconductor. If we get a negative charge in metal, we get positive charge in semiconductor. So this is the first assumption, and we assume there is no additional interface charge. And the second assumption is that there is no carrier transport of the insulator under DC biasing. That means your insulator is perfect insulator, and then the resistance or resistivity of this insulator should be infinite. So we can consider it is a perfect capacitance. We can isolate this opposite charge in either metal or semiconductor. So it is a way to control the corresponding charge distribution. So that is also a way that we can have a variable capacitance in this structure. So this is easy to identify. So we can just have a silicon wafer, and then we do the oxidation. And then we just connect with both layers with the metal connection, either the ohmic contact and the Schottky barrier. And then we can see what is the capacitance change. So it is the most widely used metal insulator semiconductor capacitor. That's what we mentioned. And then later on, we combine it with additional channel, we will realize the transistor with the MIS system. So in Venn diagram, as we previously mentioned, Venn diagram is always the most important part. So the first one is that, as we mentioned, that the metals, we have the work function from the Fermi level of the C level of electrons to the vacuum level. So you get the phi n. And then times we previously have the semiconductor with different doping. For instance, we get left figure is the N-type doping. The right figure is the P-type doping. So you can see the Fermi level is on top of the intrinsic layer for N-type semiconductor. And then for P-type ones, the Fermi level is below the intrinsic layer. So the separations give you the corresponding potential. So we get the phi s indicating the work functions from semiconductor N-type doping. And also we get the electron affinities from the conduction band. So you get the corresponding phi s, which is the electron affinity, and the phi n, which is the potential between the Fermi level and the conduction band. And for this case, you can assume it will depend on several factors. The first factor is what is the corresponding work function of metal, and what is the work function for semiconductor, and what is the electron affinity, and how much doping we have. It will change the Fermi level. So you can think it. There will be a potential in between the semiconductor insulator and the metal. If you do not have a ideal one. And then the two figures showed here, we give you an ideal case. What is the ideal case? We have the work function in which the metal work function aligned exactly with the semiconductor work function. So we can think phi m equals to phi s. What does this mean? This means you, without additional voltage or band bending, we get a Fermi level aligned both in semiconductor and the metal. So that means that the Fermi level is initially aligned, just like we talked about p-n junction. If there is no additional external potential, the Fermi level will be just like a flat C level on both p-type and n-type. And here it works like the same way. So you get the semiconductor with the n-type semiconductors, and we get the metal aligned with the same Fermi level without external biasing. And for this ideal case, since we assume the work function are both the same in metal and the semiconductor, so the Fermi levels will perfectly align without any band bending. So you can see the band structure is also a flat structure or stranded one. And then it works for both p-type and n-type as long as we get the Fermi level aligned with your work function of metal. So for this ideal case, no matter how you dope it or how do you adjust your material, as long as we have the work function from the Fermi levels to vacuum level, the same with the connecting metal, we should assume that it is a perfect case. And then in the skin or in the electronic device figure, you can assume these figures to be like the metal semiconductor insulator and the semiconductor connection. And with schemes, we can apply the voltage from metal to semiconductor and assumes the voltage biasing direction is from, if it is positive, it means the metal has higher voltage than the semiconductor voltage. So we are able to first build up a really simple architecture to discuss what will happen later on if you get additional voltage. And then you may notice that in between the insulators, we get additional electron affinities, the tie insulator, so indicating that we have a strong barrier. So that also verifies that our previous assumption, if there's no additional events with additional voltage, there should be a really strong boundary to separate the charge in between the metal and the semiconductor. Okay, and how about the other way? We try to accumulate or apply the additional voltage on the metal plate. So as we mentioned, we define the structures that the voltage applied to the metal should be higher than that applied on both semiconductor in between the insulator. So by these schemes, you can assume that when we apply the positive voltage, that means you get additional electric field from metal to to semiconductor. So no matter it is for N-type or P-type semiconductors, we always have the same action from metal to semiconductor. So you can see the band bending. And as we previously mentioned, if you get additional voltage, no matter it is positive or negative, you get the Fermi level split in between these two junctions. So you can see that the electron affinity, the work functions are still the same. So you can entirely shift the total band structure for semiconductor metal. So in order to produce the electric field in between these two junctions, we get this band shift away with each other, and the potential difference from the Fermi level between metal and the semiconductor equals to the voltage you apply externally. So after the external charge, you can see that the Fermi level will still remain a flat one in semiconductor. However, the band structures will alter because we get the electric field. So in between the carrier accumulation region or the junction region, you can see the same slope of this function, and this slope equals to how much electric field we can have. And the more voltage you applied, we get a stronger electric field, and we get a abrupt slope for this junction layer. And then after this bending, you may notice that the Fermi level will be still flat. So you can think what happened here is that we get the band bending. And then as we mentioned, these band bending structures will allow you accumulate a more electrons along the surface. The reason is because we get the band down, and the electron seems to be moved forward because we get the electric field from metal to semiconductor, from left to right. So when applying this left to right, you can see if you have any free electron from semiconductor side, it will inject from from right to left. But under these circumstances, we have a perfect insulator in between the metal and the semiconductor. So all of the electric field effect will only apply in semiconductor. So the electrons will be trapped in between the junction of insulator and the semiconductor. And then this can be also verified what is the corresponding position of the Fermi level. So if you look at the Fermi level within initial doping concentration, you get the difference between conduction band and the Fermi level. And we can note it is phi n. And these phi n's will be smaller along the surface. That means your Fermi level approaches to conduction band and move upwards to the intrinsic level. That means you accumulate or seems to be effectively have more dopant concentration. And these dopants will be N-type, or you can see it is electron. So in the N-type system, if you apply the voltage, which is larger than 0, more voltage in the metal side, you get the accumulations of the electron, and under the skin, you pull away the free hole in valence band. So you get these separations of the electron, and even the hole is a minority carrier. So most of the conducting carriers will be electron. And of course, what happened here is in metal, there will be positive charge accumulating along the surface. Okay, so you can think that we have the electric field. The hole will follow the direction of the electric field. So it will float from left to right, and it will meet the boundary between the metal and the insulator. So there will be accumulation of the positive charge. So under the skins that we have the N-type semiconductor connection with the insulator and the metals, we get accumulations of the negative charge and by applying the positive voltage. And how about the other side? In the previous slide, we have the P-type system, and for the P-type system, we get the hole initially as the majority carrier. However, when we apply the positive voltage along the metal plate, you may notice that the electric field still along from left to right. So under these schemes, you can see the accumulations of large positive charge will be still here, and we still get the negative charge here. But you may notice that for P-type semiconductor, the majority carrier should be hole carrier. So for hole carrier, the minority carrier will be electron. That means that along the surface, initially we have a lot of hole, but at that times the hole will be depleted because, as we mentioned, the hole will be pulled over from the surface with the electric field action. And the minority carriers will start to appear. So the number of the here's we get the electron as the majority carrier. So the number is more than the p-type system. However, for p-type system, as long as we get a strong field, stronger voltage applied in the metal, we still get a potential in generating the negative charge or electron along the surface. So you can think that the Fermi level apparently initially get the Fermi level below the intrinsic layer. That means you get more hole concentration. But later on with the applied voltage, do we get the Fermi level still as a constant because we mentioned it is just like a sea level. But for the intrinsic level and the entire band structure, it will bend down. When it bend down, you get this intrinsic level close to the Fermi level. That means your semiconductor move from p-type to intrinsic type without doping. And then later on, if you apply a stronger voltage, you get a more bending along the band structure. That will give you a potential that this intrinsic level will go down even below the Fermi level. That will give you some inversion layer. That means you change your p-type system to n-type system. So under the schemes, if you apply the positive voltage on the metal plate, for n-type semiconductor, the connections along the surface will give you accumulation, in which we get more electrons along the surface in n-type region. And in p-type regions, we can denote these electrons will cancel out the majority carrier along the surface, so we call it the depletion type. And the even more stronger field applied to the surface, we get the inversion one, in which we change the polarity of semiconductor from p-type to n-type. So this is a really simple case. As we previously mentioned, there will be some assumption. The first assumption is that there will be only charge existing along the metal and the semiconductor. The insulators are perfect. And also, do we get the positive we get the work function aligned with the work function in semiconductor, so there will be no additional bending between the insulator and the semiconductor. So that is a really general case. So we understand that we have three different conditions by applying the positive charge for both n-type and the p-type region. For n-type region, we get accumulation. For p-type regions, we get depletions or inversion layer. Okay. So how about on the other side? So we get the negative charge on the metal layer. So even we define the voltage here is just like a positive charge, but you can assume this voltage is less than 0, is negative. So under the skin, again, we get the electric field from right to left. So you get a positive charge here. So you can consider we still keep the same working function in electron affinity, and also the work function in semiconductor. So now we still get the Fermi level split between the metal and the semiconductor. And this Fermi level in the semiconductor should be still like a sea level as a flat one. But the band diagrams will bend along with the electric field, so it bend up. When it bend up, the situation changes. So in n-type region, you can think that the Fermi level approaching to intrinsic level closer. That means you move the n-type systems to neutral system. That give you like a cancellation in both free electron and hole. So we get accumulations of the charge in hole. So you can think that this bending will allow you a negative charge move on the other side to the right, but the positive charge will move along and then accumulating along the surface of insulator. But since we are working with n-type systems, so this hole accumulating along the surface will bend the structures to intrinsic level. And these ones will give you 0 charge along the surface. So you get this mobility. That's what we call the depletion region. We got the surface without any free hole and electron. And if you get applying more negative charge, so that give you more bending along the surface. What happened here is that it's possible to move this intrinsic level more upwards to Fermi level. Then the Fermi level will below the intrinsic level. What does this mean? This means your semiconductor will change to p-type system. So that's what we call the inversion layer. Okay. And how about in the original p-type system? For p-type systems, that would be interesting to see if you get the accumulation still the same bending with the negative charge. With these bending structures, you may get accumulation still the positive charge along the surface. And since it is a p-type semiconductor system, that means you get more charge accumulation, whole accumulations along the surface. And the electrons will be pushed away. And under these schemes, the intrinsic level is originally above the Fermi level. So after the bend up, you get this separation stronger. That means you get the Fermi level more close to the valence band. And this means you get more p-type doping. Or you can say that the effective doping concentration increase. The reason is because, as we mentioned, we have the accumulations of these positive charge along the surface. Okay, so under these schemes in p-type with the negative charge, we call it the accumulation. So still, if you compare with the previous slide in n-type system, if you apply the with positive charge, we get the electron accumulation along the surface. But for the p-type systems with the negative charge, we get the accumulation along the surface in p-type semiconductor. And also for depletion or inversions, we need a negative charge for n-type system. And in the previous slide, we need to use the positive charge in the p-type system. So that gives you a general hint if you want to operate the band structure of the metal oxide semiconductor connection, what is the positive and the negative charge you should use under this constant. And also, as we previously mentioned, it still assumes the work function between metal and the semiconductor are perfect. So under the schemes, you can consider that the difference between the Fermi level between metal and the semiconductors will be exactly the same with the voltage we applied under the metal oxide semiconductor scheme, or MIS scheme. And also, even we use oxide as an example, but if you work with different materials like sulfide material, we can think that the applied materials could be GaN oxide or different insulator. So that will work as a metal insulator semiconductor MI system. Okay, so within these systems, as we mentioned, since there is no additional current, unlike those in p-n junction, we get the penetration between hole and the electron. So we get the I multiplied with expander V applied voltage over Vt. So under that schemes, we get currents on the different positive charge and the negative charge. But here's if you get a perfect insulator, it works like a capacitor. So the capacitance will get the separate charge on the scheme. So even without talking about more detail about the variable capacitor, you can consider what is the accumulation charge. If you are able to accumulate more charge, that means you get a higher capacitance. And for these conditions, you can think that if you are working with depletions or inversion region, no matter in p-type or n-type system, depending on what is the positive or negative charge we apply, you get least charge accumulating along the surface. That means your capacitance is less. If you work with the accumulation region, that means your charge accumulation along the surface will be stronger. And under the schemes, we get a higher capacitance. So even without change the capacity between the metal and the semiconductor, without changing the material of the insulator, without changing the distance of the capacitance or the width of this capacitance, we can get a different capacitance by applying the positive or negative charge, and also using with the p-type and n-type system. So that is the traditional way, as we mentioned, in the middle of 1915s, we get the variable capacitance using the metal insulator semiconductor. And it could be simple because the only difference between the conventional capacitance is that for conventional capacitance, we use metal insulator and the metal. So that is the regular one. And then now we try to insert additional semiconductor in between the metal and the insulator. And then we can get a positive charge for higher capacitance in the n-type region because we get the accumulation region. And then in the p-type regions, if you want to apply it with the larger capacitance, you need to apply it with the negative charge in order to have accumulation condition. So we will later talk more in detail about why we applied with different voltage and how do we control it as a transistor. But let us take a p-type systems as an example. So since there's no current flowing through the metal insulator semiconductor process, as we previously mentioned, the insulator seems to be a perfect one, so there will be no variation from the level within the semiconductor. So under these schemes, as we previously mentioned, the Fermi level seems to be a flat one without any difference. Okay. And then for accumulations, in which in p-type system, do we want to have more hole along the surface? So under that constants, you need to have the Fermi level well below the intrinsic layer. That means effectively, we get a higher n-type p-type doping. So you get the Fermi level moving closer to the valence band. And these p-type systems will indicating larger hole concentration along the surface and effectively seems to be has higher doping in p-type semiconductor. And how about in depletion type? If you are working with depletion types, the Fermi level will be the same on with the intrinsic level. So the Fermi level will move closer to the intrinsic level along the surface, indicating the neutralizations of the free electron and hole. So what is the level of intrinsic level? Typically for silicon, it will be 1.4 1.5 multiplied with 10 to 5, 10 to 10, and then that will give you the intrinsic one with this free carrier. And for inversion one, that means you move change the polarity of the semiconductor. For instance, you get more negative charge in p-type system, especially with more depletion hole near the surface. So this will leaving behind the uncompensated iron acceptor. And as we previously mentioned, if you move the electrons, that means you get positive charge along the surface. But typically, you do not have additional positive iron along the surface. So it just accumulates the meiotic carrier from the other side to accumulating along the surface. Okay. And the n-type levels is not formed by doping. It's just like inversionally, originally from the p-type semiconductor with applied voltage. So it is a really important point. So if you want to look ahead why we have surface charge or the n-type after inversion layer. So we talk of the p-type as example, but why we can have the n-type level along the surface. The reason is because we build up an internal electric field. So we accumulate more meiotic carrier from the bulk material, the bulk p-type semiconductor. Once we accumulate the meiotic carrier along the surface, that will give you the increasement of the effective electron concentration. So that will give you the inversions of the original p-type semiconductor, but it doesn't guarantee that we form it by doping. So you can think the doping along the surface will be still p-type, but the accumulations of this minority carrier give you more accumulations along more electron concentration along the surface. That is the most important part. Okay, so we already talked about the ideas that we have the same metal and the semiconductors, and then we can identify what is the corresponding scheme in order to get the structure work out. Okay. So next we consider the second condition. So in order to upload the video online, I want to change and try to separate the record into two different sections later on. So we previously mentioned that in the schemes that we have the electron affinity or work function the same for both metal and the semiconductor. So we do not have any bending in between the system. That is the ideal case. So if you look back to the original case without applying any external biasing, you get exactly the same Fermi level in between the metal and the semiconductor. However, in most of the case, even if we work with the practical semiconductor doping metal, what happened here is that typically you have different ways, so you get a different work function. So let us first look at the slide. You have the slide there, and I will show some graph to compare it with the scheme. So in most of the case, maybe first define what's the regimes that I want to use here. Okay. So what we typically have is that if you work with different functions, typically we have the phi n, which is not equal to phi x. Okay, so that means you get a different work function between the semiconductor and the metal. And then under that scheme, so we still try to draw the metal insulator. So here is the insulator. Okay, so under that thing, I hope this is clear. So with this insulator, let us first assume what is the condition here. So we assume that the metal work function is less than that in semiconductor. So what does this mean? This means that if you have a vacuum label, which is on top of this layer, so here's the vacuum. So ideally, we get the work function defined in metal, which is here. So it is phi n. Okay, you can consider the electron C label is here. And then after insulators, we get the semiconductor, and for semiconductor, we get the electron. So the phase, the phase, which is you can see what is the definition. It is the Fermi level to the vacuum level, right? So if you go back to our previous slide, here's the Fermi level. From Fermi levels to vacuum level, we get the phase. This one is larger than that in metal. Okay. So under that constant, we can sorry, so let me check the record. Okay. So under that constant, we can simply view have these two connections. So here is the semiconductor. What happened here is that it seems to be not nature. It is not a 9-hour theory because the Fermi level seems to be offset with each other. Okay, so we should have also draw what is the corresponding. So define maybe still with the p-type semiconductor. So we call it the p-type semiconductor. Okay, so if you work with the p-type semiconductor, the Fermi level will be lower maybe than the intrinsic layer. Okay, so here is the intrinsic layer. And for the intrinsic layer, it should be pretty close in the middle of the conduction and the valence band. So we can draw, here is the conduction band, and here is the valence band. So here is the entire band structure. So for this entire band structure, you can clearly see that it is the Fermi level doesn't align, and then you get a voltage in between of it. Okay. And then it is not nature, so we want to align it, just like you get a 2p-n junction. Once you connect with 2p-n junction, the Fermi level is not aligned. It is not a nature, and it is not aligned. So what happens in p-n junction? There will be a building potential initially, and you can see there will be a free electron move around. So you align the Fermi level in p-n junction, and at that time you introduce an internal electric field. Similar thing happened in metal insulator semiconductor connection. So what happened here is even we do not have the exchange of the free electron in the hole. We have the accumulations along the surface. Once you have the accumulation of the electron in the hole, you get an electric field charge in between the insulator. So that is the way we did here. So the first thing is that we need to align the Fermi level from here to here. So you can think that we first part still maybe align the metal layer here. So in between the insulator, we get the metal, still the work function of metal by n. And here there will be bias. Okay. So as we mentioned, the bias is larger than phi m, so you can see the vacuum level should be bent up. Okay. So your vacuum levels will be the dashed line here, and this vacuum level will bend up upward. Okay. So after considering this Fermi level, you can draw the corresponding position of the conduction, intrinsic level, and the valence band. So again, we try to draw the intrinsic layer, Fermi level, So you can see the work function of metal will be exactly the same level along the Fermi level in semiconductor. Okay. And also, do we try to draw the valence band, conduction band? Okay, so how do we do the connection in between two? So how does this change in between the insulator and the semiconductor? So the idea is that we have the build out the electric field, and all of the band structures should be in parallel together and impact with this electric field. So what happens here is we still draw the insulator with the band bending, and we get an electric field from left to right. Okay, so if you have this condition, of course, you can think what happened here is that once you get the electric field from left to right, that means you get a charge accumulation along the surface. Okay, so you can see that along the surface, what happened here is that we get a certain accumulation along the positive charge in the metal, and also do we get the band up, band down here because we need to have the same slope along the surface. Okay, so everything bent down except for the Fermi level because as we mentioned, Fermi level is a state level. It should be entirely flat. Okay, as long as we do not have extra external biasing. So under that scheme, so we get the same Fermi level along with the metal layer. And then so we get the accumulations of the electric field. Because when you consider the electric accumulation of the charge, so you can consider the charge trapped. Here it will be -1, which is hole, which is electron, sorry. So we get some electron accumulating here. And since the electron in the p-type region, still the p-type region, will be magnetic carrier. So you can consider the magnetic carrier will first accumulating to cancel out the majority carrier. So here we get the p-type region, we get the majority carrier as the whole carrier. We get a cancellation or depletion in between these regions. And for this one, you can think that for the band structure, it will accumulate like this one. As we previously mentioned, we get a negative charge, we get positive charge, so we get an electric field from left to right. But the next thing is that what happened is that if you want to talk about the band diagram or talk about the previous slide, what should we have or what it should look like? You need to apply the voltage in order to further discuss. So for instance, we previously mentioned what is the depletion position, what is the accumulation position. So for that circumstance, we had better to start with the flat band in order to judge if this structure is accumulation or depletion or inversion. Okay, so let's do these things. So I want to first use start the rater in order to